All right, let's dive right into this explainer. We're going to uncover why precision in manufacturing is, well, it's a whole lot more than just a company writing a massive check for a fancy machine. If you're in procurement, if you're a brand owner, or honestly, if you're just fascinated by how things are actually made at scale, you are absolutely in the right place. Today, we're tearing down that shiny factory marketing facade and getting right into the undeniable physics of manufacturing.
We've all seen it, right? You flip through a supplier's brochure and that buzzword, precision. It's just plastered on literally every single page. But let's shatter a huge myth right out of the gate. Buying high-cost equipment absolutely does not automatically guarantee perfect parts. In reality, turning accuracy is a strictly quantifiable, highly technical requirement. It directly impacts your assembly process, the lifespan of your product, and, at the end of the day, your brand's entire reputation. True precision? It takes active, relentless management from the supplier.
So what are we actually talking about when we throw around the word precision in CNC machining? Well, it all boils down to turning accuracy. Basically, how closely does that piece of metal coming off the line actually match your blueprint? Achieving this conformity isn't just hitting a big green go button. It's a highly complex, interconnected ecosystem. Think of it as a super delicate balancing act involving mechanical, environmental, and process-related variables.
Okay, here's our roadmap for today's explainer. 1. The macro elements. 2. Thermal deformation. 3. The microcut. And finally, 4. The 2026 audit.
Let's jump straight into Section 1, the macro elements, machine tool geometry.
Just let that number sink in for a second. Plus or minus 0.005 millimeters. When we're sourcing high-precision components, this is the microscopic tolerance we're demanding. It's incredibly tight, and at this level, your foundational factor is the inherent geometric health of the CNC lathe itself. If the machine's actual physical skeleton is out of alignment, well, every single part it spits out is going to carry those exact same errors. No way around it.
So if that machine's skeleton is misaligned, you're going to see it pop up in three main ways. First up is spindle runout. This is basically when the spindle deviates from its perfect axis of rotation, which gives you these super frustrating roundness errors and just awful surface finishes. You definitely need to be asking for the spindle's total indicator reading. Second is guideway parallelism. If the carriage doesn't move perfectly parallel to the spindle, you get what we call tapering, so your supposedly perfect cylinder ends up having a different diameter at each end. And finally, positioning accuracy. Over time, ball screws just wear down. This leads to backlash, which is basically lost motion when the tool reverses direction. It's a massive culprit behind dimensional inconsistency.
Moving on to Section 2, thermal deformation, the invisible killer.
Now, there is a silent danger lurking in literally every factory, and that's thermal deformation. As a CNC lathe runs, the internal friction in its motors, the bearings, the hydraulics, it generates some seriously intense heat. And that heat causes the machine's metal components to physically expand. It's crazy, but a spindle can actually grow several microns in length over just a 4-hour shift. If your supplier isn't actively managing this, the parts they produce on a cold machine at 8 a.m. are going to be wildly different from the parts they run at noon.
So, here's a massive pro tip for the next time you're walking a factory floor. This is the exact question you need to ask to test your supplier's technical chops. Don't just stare at the shiny machines. Look them in the eye and ask point blank, how do you manage thermal drift?
The thing is, leading OEM manufacturers don't just cross their fingers and rely on luck or ambient room temperature. They proactively fight that cutting heat. They're implementing strict machine warm-up protocols. They're using climate-controlled workshops. Or, investing in advanced real-time thermal compensation software. They also heavily manage the actual cutting heat, that's the friction between the tool and the workpiece, using very specific coolants and pressures. Without all of this, your workpiece just expands during the cut and then shrinks back down once it cools off on the shipping truck, and you're left holding a box of totally useless, undersized parts.
All right, Section 3, the microcut, tooling and rigidity. Because listen, even the absolute best, perfectly temperature-controlled lathe is going to fail if the microdynamics are off. Take rigidity, for example. If a part is long and thin, meaning it has a high slenderness ratio, it's literally going to bend away from the tool unless they use a steady wrist. And what about clamping force? If an operator over-tightens a hydraulic chuck on a thin-walled part, it gets deformed right then and there. When they release it, pop, it springs back into an oval. Then you've got the material itself. Cold-rolled metals actually have internal stresses that warp the part as the outer layers get shaved off. And of course, tool wear. As that cutting edge dulls, the cutting forces just skyrocket. The really high-quality suppliers are using automated tool life management systems to swap out those tools way before this kind of tolerance creep even happens.
Then we get to the programming, which is basically the exact recipe for the cut. Getting this wrong spells absolute disaster. If the feed rate is too high, you completely trash the surface finish with these large scallop heights. If the cutting speed is too low for the material you're working with, you run into what's known as a built-up edge. This is wild. It's where tiny little microscopic bits of the workpiece actually weld themselves straight onto the cutting tool, which causes sudden, totally unacceptable dimensional jumps. And if the depth of cut is too deep on a roughing pass, it actually deflects the spindle, and the machine just can't correct that error on the final finishing pass.
You might want to take a screenshot right now. This is kind of your ultimate sourcing cheat sheet. It synthesizes all the variables we've just been talking about, categorizing everything from the machine tool right down to the process itself. If you look at the procurement concern column, you'll know exactly which factors pose the absolute highest risk to your specific order. Like for instance, if you're ordering really slender parts, workpiece rigidity is critical. But if you're running massive long-term batches, thermal drift rockets right to the top of your priority list.
Which brings us to Section 4, the 2026 Audit, Supplier Verification.
Look, the reality of procurement is that you simply cannot physically stand there and supervise every single cut. So your audit has to verify their systems. Step 1 is checking their PM, or preventative maintenance schedules. Precision degrades as machines get older, right? You need to actually see the logs. If a machine hasn't had its guideways leveled, or if its ball screws haven't been checked for backlash in the last 3 years, well, it's highly, highly unlikely it can hold those tight tolerances we talked about.
And remember, turning accuracy is completely meaningless if a supplier can't accurately measure it in the first place. You need to be looking for coordinate measuring machines for those complex geometries, air gauging for extremely tight diameter tolerances, and surface profilometers. But the real gold standard heading into 2026? It's combining highly skilled machinists with automation. Look for something called in-process probing. This is incredibly cool. It's where the lathe uses a little touch probe to actually measure the part while it's still clamped right there in the chuck, automatically adjusting offsets on the fly to compensate for tool wear or thermal expansion.
Understanding all of this, realizing that turning accuracy is deeply, deeply influenced by mechanical alignment, thermal management, and tooling logic, that empowers you. It lets you confidently evaluate your suppliers and finally move beyond just looking at the absolute lowest bid on a spreadsheet. What you are really looking for is a true partner. Someone who acknowledges these exact variables and has established, proven protocols in place to mitigate them.
So, I want to leave you with this final thought for your next factory audit. Are they managing the ecosystem, or are they honestly just relying on the fancy brand name printed on the side of their lathe? Arm yourself with these technical insights, ask the hard questions about thermal drift and runout, and I promise you, you will fundamentally transform the reliability of your supply chain. Thanks for hanging out with me for this explainer. And remember to keep seeking out the facts behind the manufacturing facade.